Welcome to Introduction to Distributed Systems Scaling. Today I would like to tell you a story that is well known for many companies as they scaled up from a single person garage startup into international company. A story from a single computer into a distributed system. A story that starts with a single website or an application. As long as this stays static, as it cannot be modified by users, it is perfectly enough. But once you want to let users add some posts, comments, access some data only by some of them while not by others, you need to have some kind of a coordinator that will collect all their actions. I want to add this post, I want to add this comment, and return them what each of them should be able to see. This coordinator is just a computer like the one you are using towards this presentation. To make this computer a coordinator, a backend service, you need to install there a special program that will listen on your network card and respond to your requests. So this is your backend application, your application written in some programming code, PHP, Java, Kotlin, or any other backend programming language. This application by itself needs to store data somewhere, because if it would only keep it on some variables. Once your computer is turned off and on again, all the data would be gone. So it could use files to store data, but files are not optimized to store, to search for data, to quickly read and write data. So instead, the smart people made a special application called a database that is optimized to hold and find and process big amounts of data. So this is the architecture of how your backend might look like in your first startup, in your university project. You are installing some kind of a server. Maybe it's an Apache. Maybe it's based on some framework. And you need to install some database, maybe MongoDB, or maybe some SQL database like SQLite. And that is enough to respond to all your clients when they are sending requests. I would like to add this post. I would like to see the posts for this person, etc., etc. This is how many small companies, how the architecture of backend service of many small companies looks like. But this gets not enough once you are scaling up. Once you are scaling up, a few things can go wrong in here. So first of all, since everything is in a single computer, you depend on this computer. And what if this computer is turned off? Second of all, this computer might not get enough. The computer is just a computer. It has limited processor and RAM and everything. So step into into a bigger company is to extract a separate dedicated devices, to buy a special server device that is optimized to handle as a server, that is very fast, has a strong processor, lots of RAM, small but powerful disk, a fast disk. And a database can be either installed there, or even better, it can be a separate dedicated device, And this is how this is how the architecture looked like in many companies. It used to be a standard even in very big companies. There were very strong servers on one side, and there were databases. They were connected together directly so that the connection is very fast. And both devices were optimized for their purpose, so they were working pretty well. Also, such databases are easy to make a copy. So you can, if you are an insurance company or a bank, they were copying the content of their databases every once for a while, and thanks to that, if anything happened, if the place was burned or hacked or whatever, and they could always, restore the database from some point of a time. So they kept this database in a separate location, in a safe place, and this gave them some safety. This architecture is a very popular architecture. It's so-called three-tier architecture with client, server, and database. But as your number of requests are getting bigger and bigger, it is not enough, and it is not enough for a few reasons. One of them is that it's not enough for a few reasons, but those reasons can be solved in different ways. And the first intervention I would like to mention in here is to use a cache. You can see when I added cache, we have less requests to each layer. So what is cache? Cache is a redundant memory. It's a memory, like additional memory, that can always be removed and nothing is lost. So for instance, in the backend, in the server, we might have a cache before asking database and hold in this cache the most popular data that we need to ask for. Yeah? So if we have such a cache, then whenever someone asks for that, we can immediately return it from the local memory instead of asking the database. So we limited the number of requests. We also speeded up the response time. If this cache is outdated, if the data has changed, we invalidate this cache, and thanks to that, the data will never be incorrect. So the data, the cache needs to be maintained. But it's a very powerful mechanism, and it is used in all the layers. So clients also use cache before asking backend. So if they ask for something on, for instance, many pages, they might ask only once for it and keep it for all the other places. Cache is used on networks. Cache is used on your computer on many layers. Cache is used inside databases. So cache is used everywhere on many different layers. And we also often implement it by ourselves. Although often cache is not enough and we still are overloaded with data. Another intervention is vertical scaling. So it means buying a better equipment. So adding more RAM, buying a better processor, adding a better memory, maybe SSD memory. This is good for some time, but above some point you cannot move it any. It's very expensive. It gets very expensive to move it any further. If you have an average processor, buying 2 times better, that's not a big problem. But if you have one of the best processors on the market, buying 2 times better is either very expensive or not possible at all. So vertical scaling makes sense only for some time. Okay, and so we need to find another technique. There is one more problem I wanted to mention with this architecture that vertical scaling does not solve. It is that every point, the backend, the server and the database are both a single point of failure, meaning that if any of them is having some kind of trouble, maybe something happened, maybe a person who is cleaning the room accidentally unplugged it, maybe there is a fire and the location burned, whatever happened, if any of them is not working properly, then the whole backend is not responding, cannot respond. So as a result, the clients do not have a service, and your website is down. Your website and your application cannot work properly. So this is no good. I mean, this is okay if your traffic is not very high, but in a companies like Allegro where I work, even few minutes out of service would cost a huge amount of money. So we cannot let that happen. So we need to introduce another technique that will solve both problems, will help us scale our service and also improve availability. So what I want to introduce here is a vertical scaling. And thinking about server, vertical scaling means making multiple machines with the same program running, service running. So you can see that all those machines have symbolizing they have exactly the same program running on them. We also have some load balancer. So this is a device, like all the requests needs to be directed to the same IP address to our company, but then the load balancer will distribute the traffic to all the available services. One big thing is that generally you should assume that you cannot hold anything locally, because if you hold anything locally on one service, then it won't be available on another. Yeah. So everything that is important needs to be kept in the database. There are some exceptions to this rule. There is a technique that is very popular that is called consistent routing. Oh my. The idea is that the same client with the same IP or maybe with the same token will always be directed to the same machine, to the same server. Thanks to that, this machine can hold some local data. So it's better because like cache is working better because it keeps data specific to the users that are calling this particular machine. And we can also keep some data here that are not very important data, like maybe a session. So something that, okay, it's not very terrible if this is lost, but should be kept. Although this mechanism does not work well with other mechanisms that we like to introduce here. So another mechanism is auto scaling. That is, if there is more traffic, we add more machines. If there is less traffic, and there are less machines, as you can guess, vertical auto scaling does not like the consistent hashing. So in this architecture, there are some trade-offs, but I hope you can see the picture of horizontal scaling of its challenges. For now, notice that the database itself hasn't scaled yet. All the requests are sent to the database as they used to be before. So database still needs to be scaled, and such a simple scaling as you just have seen is not an option for a database. Database needs to have, it cannot hold only some data. I mean, database needs to be scaled in a different way. And there are two different techniques I would like to present you here. The first one is a master-slave architecture. The main idea here is that we, instead of one database, we make a few databases that will all have the identical data. They will all have all the data. Once we have those machines, they first need to find a master, the most important database in this architecture, and master is the one instance where all the writes are directed. So whenever we write something, we send this write request to the master, and master propagates this writes to other services, to other databases, so that they all have it. So now we have the same number of writes as before. That's clear. Yeah, they all need to have all the data, so we need to write the data to all of them. But so what's the advantage? The advantage is that the number of reads is divided by the number of databases, because read can be done on any of those databases. So of course they are not connected one-to-one. Each read is directed to a random database, and this load balancer is distributing this traffic equally. So as a result, the number of writes stays the same, but the number of reads is divided by the number of databases. And since the number of reads is generally much bigger, you can imagine you enter some website and you can see some posts and some users and some ads, and all the reads from databases. Yeah, you need to read those posts, those users, and those articles. And how often do you actually produce some data? Not very often. Yeah, so we generally have much more reads than we have writes. So this architecture is actually very useful. It's actually nicely dividing our traffic on the database. What's the trade-off? One thing you need to notice in here is that since we are first writing to the master, and just then we are writing to the slaves, there might be some inconsistencies, So if the propagation time is getting bigger because maybe the databases are overloaded, something might be on some slave while not on the other. Okay. This is sometimes strange. What is even bigger problem is when are we responding that we saved some data? So imagine that we are storing some important data. Maybe it's a financial transaction, and we are storing it into a master. Master needs to propagate it to all the slaves. Who knows how many of them are they? We are sure that those data are stored only when only when all those databases respond to us. Hey, I'm done. It's fine. I got it. Then we can surely respond to the server. Hey, operation is correct. You can accept it. Yeah. Because if we wouldn't, then the server would try to do it again. Or respond to the user that operation failed. Once we have them all, you can respond. It's fine. This is a safe option, but it's also a it takes long time, to write to all those databases. Who knows? Maybe some of those databases has some overload and needs to take a bit more time. So this is a safe but heavy option. Okay, but we could also do the opposite. So maybe we could just save to the master and respond, hey, that's fine, I will handle that, and master will propagate it to the other databases. Yeah, that's fine. It will surely propagate it to the databases, but there is a catch. What if the master is dead right now? For any reason, someone unplugged it, it's burned, whatever. It just happens. It happens in a real world situation. If you are a big company and it happens once a year, it's sure that some of the data will be on such situation. Yeah, and if this is a financial data, it can be a big problem. Okay, so if master would accept it and but wouldn't have time to propagate it, and bam, it's burned or unplugged or whatever, what happens is that a random database is chosen as a new master, and this database might not have this record, and so the data might be lost. So saving it only to the master is not safe, but it's fast. So there is different kinds of persistency you can have. All, yeah, you need to save it to all to confirm. One, you only save it to master to confirm. And there is the option in between that is very popular. It's I believe used most often. It's a majority. It means that we are responding that's fine when the majority of instances confirm that it is saved. Okay. So another technique that I would like to explain here first needs to the short explanation of the very popular algorithm that is widely used in many languages, in many places on data science, that is called hash table. I will explain it on a set. Such a set is used in most programming languages, including Java and JavaScript. A set that includes a hash table under the hood. So a set is a structure where the elements cannot repeat. So every time we do some operation, we add some element, we need to check if such element already exists on the database. So the operation of checking if set contains something is a very important operation. It needs to happen very fast. And as you know, list is not a good data structure for checking for if element is in there, because if you have a list and you want to check if the element is on this list, you need to check one after another. Yeah, so this is so-called ON complexity, because you need to check the number of elements that is proportional to the number of elements on this list. So what is set offering to us? Imagine that you have a bunch of names, maybe those are some strings. To do a hash table on that, we need to calculate some hash function on it. So most languages have some basic hash functions implemented. Hash function is actually any kind of function, any kind of function that fulfills a few rules. So first of all, and the most important rule, is that equal elements always need to have the same number returned. So if two elements are equal to each other, they need to always have the same number. So this is a consistency rule. Also, hash tables should be very fast. That's an important rule. And hash table should distribute our elements more or less evenly on the space of possible numbers. Yeah. So imagine that we have some hash table that gave us the following numbers for those strings. Okay, but out of that, I would like to make only 4 buckets. So I will make a modulo 4 on this result, and each of those numbers will have each of those strings will have a number from 0 to 3. And based on these numbers, we are building 4 buckets. This is our hash table. Hash table is having, of course, an index like any table, and on every position there is a list. It can be any kind of a list. Alex has the number 2, so it's on the position 2. You can see there is Alex on the first position, same as Ellen. Bill and Fiona has a position 3. Danny is having position 0 and Carl position 1. Okay, this is just a way how we organized our data. Okay, so organizing them is fast. It's easy, you know. Calculating hash table is fast. Modulo 4 is fast. We just need to add it to the list. That's easier than that's easy. Okay. Now, how is finding an element? So let's check if we have Gary in our Garen in our hash table. So what we first need to do is to calculate a hash table and modulo 4. This is super fast operation. Yeah, we said that hash table needs to be fast. Modulo 4 is fast. This is BAM. This is no cost at all for a computer. Okay. Next, we need to jump at this position. So jumping at the position by index is also super fast operation. Yeah, that's on the low level. It's just a pointer to the array plus the index times the size of the element, so the size of a reference to a list. Bam, that's super fast. We are here. And we just need to compare with those 2 elements. Yeah, so instead of comparing with 4 elements, we are comparing with 2 elements. There is no Garen here. Okay, how about Carl? Bam, it's a hash 1. So we very fastly calculated the number. We got in here. Bam, 1 comparison, and we got Carl. So you see, we have much less comparisons than in a list. The number of comparisons is the number of elements divided by the number of buckets. So how many buckets we chose to have. Many implementations are making this number of buckets proportional to the number of elements. It's often the same as number of elements. So thanks to that, the finding if element is there is 01. Yeah, it's immediate. We are comparing most often with 1 element, and that's it. Yeah, on average with 1 element. So finding if element is there or not, bam, immediate. And that's a really nice algorithm, very popular, used very widely in many different places, and it is also used in databases. In a database, the technique is known as database sharding. We are always also calculating a hash table. We are calculating a hash code from values that are identifying our elements. So this is most often some kind of a key. Yeah, it's most often a key. We are calculating a hash code, and this hash code tells us in what database do we expect this data to be. For instance, imagine that we have the following table that we would like to shard. We would like to, split into 2 databases. So ID will be our way to identify those elements. So we will calculate some hash function here, calculate some hash code, and spread those devices, those values to 2 separate databases. Each of those databases have different data. Yeah. The important thing is that, hey, then now we ask, give me a user with ID 3. Okay, so for a 3, we quickly calculate hash function, and we know it's in this database. Bam, it's Paul Atrida. Okay, so thanks to this technique, each database has less data, so finding data is faster. Finding data is faster. We do not need to look through all the data. You just need to check out the smaller amount of data. So this way you can divide one database into multiple smaller databases. And this technique works really well in connection with master-slave architecture. Yeah, you can each hash you can scale by making multiple instances and have master-slave architecture, and each and you can also make sharing to share your data on each of those layers. So this is the advantages of those two multiply in effective value, because the more master slaves you have, the more vertical scaling you have, the less requests you have, the more sharding you have, the less data you have in each of those databases. So those two truly work well together. Okay, so this is how we can, those are the main techniques of scaling databases. This is important to know about. And the last important thing, because we actually know pretty well how to scale a single service. But now the question is how to scale our company, because the big problem that microservices respond to is when multiple teams need to work on the same product. If they work on the same service, on the same backend application, wow, that's often a cause of many problems. You know, if they work on the same code and they do not understand each other business rules, requirements, then that's a huge you know, a huge space for errors and mistakes and problems. So a good technique that helps us with that is to use microservices. Microservices in microservices architecture, we divide our system into separate microservices. You can see that separate services. You can see that those are different devices, but they also are running different programs, and the calls all are sent to those to different depending on what a client needs. The call is sent to a different service. Of course, from a perspective of these clients, they think they are sending to the same to the same website, but we have some API that is hiding that all and directing to a proper service that is responsible for responding to that call. Yeah. Each service has its own database, its own infrastructure, and those microservices are communicating with each other. And a big thing in here is that they can be maintained by different teams. One service can be given from one. The ownership can be passed from one team to another, and this helps us organize our companies much better. Is microservices a way of scaling application? I wouldn't say so. I mean, it probably is. In many cases, it probably is, but in many cases, it also isn't, because when you use microservices, you are adding this communication with those services that is costly. That is costly and that is problematic, because other services can also sometimes not respond. It's always easier to call another class or component than to call another service. Yeah. So there are some pros and some cons in terms of scaling this service. But there is definitely an advantage if you have multiple teams that they build some kind of an independence. Each of them can think about something else. So maybe one service is handling all the financial things, another one is maybe some content thing, and another one maybe some I don't know, sales or whatever. So one more thing that needs to be mentioned with microservices, and that's the last thing I would like to mention on this presentation. It's the event streaming, because when the services are calling each other via the HTTP, the service that is the services are still bound pretty tightly together, and to untie them, one very useful technique is to use event streaming, for instance, a Kafka or a Hermes. The big idea is that the Kafka accepts events and sends them to another service. For instance, imagine that B is responsible for sales, and whenever a sales happens, it needs to notify A and C. A is responsible for sending it, for preparing it to send it, and C for maybe some invoices. Yeah. So when we have a sale, we both need to make an invoice, and we need to add it to the system to send it. So if we use HTTP, B needs to know about both of them and inform them directly. That is no good that that our sales service needs to think about such thing. Our sales service would just prefer to say, "Hey, everyone, we got an event here. Someone sold something." And this is how it happens when we use Kafka. We just send an event to Kafka. Hey, sales happened, and everyone who is interested is subscribing to Kafka. So A and C are interested, so they told Kafka before, hey, if there is any sales going on, let me know. Yeah. So once the sales happen, the event knocks to A and C, and they can handle that. And here are very important mechanisms on the way. First of all, it gives us much more consistency. The Kafka guarantees to deliver this event. So maybe if A is dead for any reason, Kafka will just deliver this event later. Yeah? Kafka guarantees that it will never lose this event. So if not now, then later. Kafka will also not overload this service. So service can limit the number of events it receives. So it can say, hey, I want this amount of events per hour, and so or maybe can just not be ready to send next events. And so thanks to that, those events will just wait quietly in the Kafka queue, and will not and there is no risk that they will be lost. And yeah, no timeouts, no lost events. That's really big advantages. And that's it. If you have an architecture, if you have a big company, what we generally have is a microservice architecture with vertical scaling and database scaling, as we described. We generally use some event streaming services, and this is how this is an introduction to distributed systems. This is how a big system worked. My name is Marcin Moskała. I'm the author of Effective Kotlin and Android Development with Kotlin. I am also the creator of KT Academy, where we are where we are connecting great trainers with great workshops with big companies. So if you need a workshop, go into kt.academy. And I learned all of that in Allegro, where I also work. Allegro is the biggest tech company as far as I'm concerned in the Polish market. It's the Amazon and eBay of Poland. And this is a great company where you can truly learn a lot about many things. So this is, I believe, if you want to develop yourself as a programmer, this is one of if one of the best places to go. It's like on a daily basis, I use at least 5 different languages over there. So that's a really cool place to be. And it loves Kotlin. Most of the code on backend services right now is written in Kotlin in Allegro. Okay, so that's it. That was the introduction to distributed system scaling. I hope you enjoyed it, and I hope to see you next. And see you. Have a nice coding.